All right, yeah, welcome back from spring break. Let's start by thinking a little bit about the schedule for upcoming days here. So today is Monday the 23rd. What's coming up? We have exam 2 in 1 week. For you guys here, the face-to-face class, we're going to be next Monday. And again, we'll start at 9 instead of 9:05. You'll have an hour and 45 minutes to go to 10:45. And the online class, you're going to go either next Monday the 30th or next Tuesday the 31st. Calculator and note card allowed. I sent you some information about some of the problems that I put in the test so far. There will be a few more problems that I have not put on there yet. And I'll send you information about those problems when I actually finish writing the test. Also have another break, another long break, Good Friday and Easter break. So we have Friday, April 3rd off, as well as the Monday after Easter, April 6th off. So we have class, the test next Monday, and then a class next Wednesday, then a week before the next class. Wednesday, the 8th would be the next class after that point. What are today's topics? Well, first, before we get into that, here's a note. You should make sure, as I commented on Moodle, that you review the use of NDSolve and NDSolveValue in old videos, because there are going to be on the test that you have to use either NDSolve or NDSolveValue. NDSolveValue, recall, was easier to use, but we found that NDSolve was a little bit more flexible to allow us to change initial conditions with the locator, for example. So that's something that you should review by looking at the old video lectures. All right, what are we going to do today? We're going to talk about some abstract properties. Ultimately, we're trying to get to this one down here. These two facts that you see here. First, one of them says that if y1 and y2 are two solutions of a linear system, y dt equals a times y. We're thinking of two-dimensional systems, but actually this is true even in higher dimensional systems. Then an arbitrary linear combination of them is also a solution. So is an arbitrary linear combination. A linear combination of two vectors is a scalar times the first vector plus another scalar times the second vector. That's called a linear combination of those two vectors. And yes, if y1 and y2 are two solutions, then so is that. Moreover, if you've got two solutions of a 2x2 system, two-dimensional system, that are also linearly independent, which in the two-dimensional case means they're not scalar multiples of each other, then any solution of this equation can be written in this form. Okay, and we'll see that that's a consequence of the uniqueness theorem. I'm going to try to focus on proving this thing here, which, by the way, is a possible proof, that type of proof that can come up on the test. Okay, there will be one proof on the test, and that's a possible type that could come up in the test. It's related to two properties about derivatives and matrix multiplication. First of all, the fact that the derivative is what's called a linear operator or a linear transformation. If you take the derivative of the sum of two functions, the answer is the sum of their derivatives. If you take the derivative of a constant times a function, then that's the same as the constant times the derivative of the function. These are facts you knew from Calculus 1, though here we're stating them in vector form. More generally, if you take the derivative of an arbitrary linear combination like this, so we have a summation, ki is a constant, yi is a function of t. If you wrote such a linear combination out by hand, you'd write it with dot, dot, dots. You'd write it as k1, y1 of t plus k2, y2 of t, etc. Put the dot, dot, dots there. Kn, yn of t. That's how you'd write out in expanded form what that summation symbol up there means. If you take the derivative of a sum like this, you can essentially take the same linear combination of the derivatives of the functions themselves. That's what this says. Okay, so if I take the derivative of what I wrote on the board, I can just differentiate each of the y's and write the same kind of linear combination. I'll go ahead and write it here. Take the derivative of this. That can be done by taking the derivative of each function individually and then forming the analogous linear combination. important properties from calculus. You kind of use them without thinking about them, right? You take the derivative of t squared plus t, you get 2t plus 1. You use that kind of property without thinking about it. It's very fundamental to calculus working in the way that it does, and to differential equations. Matrix multiplication also defines a linear transformation. It satisfies similar kinds of properties. A matrix A times the sum of two vectors v plus w is the sum of the two vectors AB and AW. Likewise, A times KV, the K can be factored out, so to speak, and you get K times AB. More generally, you get this. How would you prove something like this in, say, a 2-by-2 situation? You can let A be an arbitrary 2-by-2 matrix, and let V be an arbitrary vector, and W be some other arbitrary vector, and use what matrix multiplication times a vector means to verify that symbolically. You can calculate A times V plus W. By replacing A with that, replacing V with this and W with this, and then adding vectors component by component. I guess we haven't really talked about adding vectors, but that's how you can do it symbolically, and it makes intuitive sense. If you add these two vectors, you get a new vector whose first component is the sum of the first components of the two vectors, x plus u, and whose second component is the sum of the second components, y plus v. Now multiply this out. A little confusing. This is a vector. This has just got two components here. Remember how I said to multiply this? Take the first row of the matrix, take the first entry, A, multiply times the first entry there, and then add the product of the second entry with that second entry. And that'll be the first entry of the product. The product is going to be a vector, so you get A times x plus u plus b times y plus v. Make sure you look at that and check in your mind that you could do that. A times x plus u plus b times y plus v. In effect, I called that the dot product of the first row with this vector. And then for the second entry of the product, take the second row and do the same kind of thing. Take its dot product with this vector, c times x plus u plus d times y plus v. Let's just leave that as is. I could distribute the a, b, c, and d through the parentheses in there. Let's just leave it as it is for the moment. And up here, let's also compute AB plus AW. Let's see what we get. The claim is, come back over here, the claim is you should get the same thing. A times V plus W should equal AB plus AW. In effect, it's kind of an order of operations thing. On this side of the equation, technically speaking, V plus W should get done first before you multiply by A. And on this side of the equation, you're multiplying by A first before you add. And this linearity is saying it doesn't matter which way you do it, you get the same answer. But we need to check that. A, B, C, D is capital A. X, Y is V. Again, A, B, C, D is capital A. And now U, V is the vector W. I probably shouldn't have used U and V, I realized. I'm using V for two different things. But that's a number and that's a vector right there. Do the multiplication. Hopefully you can do that pretty quickly now. AX plus BY, CX plus DY. That's this product right here. Now do this product. AU plus BV and CU plus DV. Now add those vectors. Do a little rearranging. AX plus AU plus by plus bv, cx plus cu plus dy plus dv. I did a little rearranging to help make the connection here. These two things are the same thing. Right, check that over by the distributive property. Okay. Technically, I haven't written this as a proof because I haven't written sentences. Really, you should write sentences in proofs. Proofs are arguments. But this is the idea. Okay? Let capital A equal something, capital B equal something, capital W equal something, abstract, arbitrary, 2x2 case though. And you would want to put this kind of equation in a sentence structure. You could say, by the definition of vector addition and matrix multiplication is the reasons that you can give along this line. And same kind of reasons here, by definition of vector addition and matrix multiplication. First we did the matrix multiplication times the vector, then we did the vector addition. And then finally it's the distributive property for real numbers that connects these two vectors and says they're equal. Okay, so that's an example of something you should be able to do. You should also be able to do the proof of this fact, which uses what we just proved. If y1 and y2 are two solutions of a linear system, dy dt equals a times y, then so is an arbitrary linear combination. How would you prove something like that? Again, I won't take the time to write sentences for time's sake here. But the idea is, well, you need to plug it into the differential equation. You need to, as always, show the left-hand side and the right-hand side simplified to the same thing. And you do need to use the assumptions you're making. What are we assuming? We're assuming y1 and y2 themselves are solutions. That's got to be important. We wouldn't assume it if we didn't need them. So that's always a key thing to look for. So here is the left-hand side, unsimplified, when you plug in this linear combination into the left-hand side of the differential equation. Here's the differential equation. I'm replacing the y in the left-hand side with this linear combination, and its derivative, by linearity of differentiation. The fact that the derivative operator is a linear transformation. I haven't defined what a linear transformation is, but in this context it means that you get this. That's a fact about derivatives. Do you get the same thing when you substitute the function into the right-hand side? Or better, what's the reason? Why would we get the same thing? If I asked you for a verbal reason why I'm going to get the same thing here, it's two steps, two reasons really. What's the reason for this step right here? Why can I do that? Yeah, well, can you say it again?
You define it right there.
Yeah, that is the right-hand side, but also, what did we just do here that I erased?
Prove that that's true. So
You proved that you can do this. That matrix multiplication defines a linear transformation, that you can do this. That's what I used in writing them. Doesn't matter that y1 and y2 are functions of t. For any fixed t, they are vectors, specific vectors, and therefore I can use that. Why can I finally say that I get the same thing right there? What's the reason for that? Why can I put this thing here as well? What did I say just a minute and a half ago about was looking at the statement here. I said you got to use your assumptions. You're assuming y1 and y2 are solutions. Therefore, when you plug them into the differential equation, left-hand side equals right-hand side for all t. So that y1 prime of t equals that for all t. And this, y2 prime of t, equals this for all t. The assumptions is the reason that we get the equality between these two things. So you should mention it based on the assumption. Okay, so there's lots of subtleties going on when you try to think about proofs. You got to think about what you're assuming, you got to think about what you know, and then you got to put them together. And it's typically a hard thing, but we work at it. Okay, we try to get better at it. You should try to work at writing this kind of thing out in sentences, in a nice explanation. It's a type of proof that possibly could be on the exam. I might modify it a bit. Maybe I'd put a minus sign in there. Maybe I'd put specific constants. Maybe I'd do a more general linear combination. More than 2 functions, maybe 5 functions or n functions. Okay. We'll do some other proofs this week, Wednesday and Friday as well, of possible types of proofs that could be on the exam. And I think that in terms of what type of proof, I won't say exactly what the proof will be about, but I'll say the types of proofs that you can expect, and this is one type right now. So make sure you think about it, and the book does discuss it. All right, I guess I should have gone over what we were doing today before I went into more details here. What else are we doing today? Let's do an example, a concrete example, that's going to generate a sink at the origin. It's going to be what I call a real non-spiral sink. We've seen spiral sinks before with nonlinear systems. This one's not going to do any spiraling. But we want to try to get a nice phase plane by finding not just straight line solutions with eigenvalues and eigenvectors, but also I'm going to use nullclines to help me draw a better picture. And I'm going to try to do it completely by hand, and then we'll see how it looks compared to what the computer produces. You want to get tangencies of solutions correct, which can happen when you have non-spiral sinks or sources. You can have tangencies of solutions as you approach the origin, either as t goes to infinity for sinks, or as t goes to minus infinity for sources. You can have tangencies along some line near the origin. You want to get those right. Also want to talk about something called the matrix exponential. Its relationships to solutions of initial value problems and flows. We're going to do all this for the sink example. And if we have time, we'll talk about some generalities a little bit more, something called the characteristic polynomial. If we don't get to that today, we'll do it on Wednesday. All right, so let's consider this example here. Let's see how far we can get with this by hand. Can we find the eigenvalues and eigenvectors by hand? We should be able to, at least if the numbers turn out nicely. And can we draw a nice phase plane by hand? Just stepped on my shoelace here. Better tie it so I don't trip. There we go. So the matrix here is 2, 7, -4, -9. I claim this is going to generate a sink at the origin. First of all, the origin is the only equilibrium solution because, quick reason, based on doing a quick calculation. That's true, the columns are not multiples of each other. That's one reason you could give, or based on, what am I doing with my fingers here? Determinant. The determinant of the matrix is non-zero. Determinant of A is 2 times -9 minus -4 times 7. Careful about negative signs here. -18 plus 28. +10. Does that look right? No mistakes? The important thing is that's not equal to 0. That being non-zero is equivalent to the columns not being multiples of each other, and also the rows not being multiples of each other. And that means that 0 is the only equilibrium solution. Well, I'll call it the only equilibrium point. The constant function y equals 0 is the only equilibrium solution. 0 as a point, the origin in the phase plane, is the only equilibrium point for the phase plane. If the determinant is 0, we'll see in those situations that you have infinitely many equilibrium points for linear systems. If it's non-zero, then you only have one. The determinant of A being non-zero means that A is invertible and also non-singular. Non-singular and invertible are equivalent. If the determinant were 0, that's called non-invertible and singular. So again, that's a situation where the non switches. It's confusing that way. Invertible is equivalent to non-singular. Non-invertible is equivalent to singular. We're not really going to be able to use inverse matrices much here. I don't think we really need them much. But anyway, this is just something to know. Why the terminology in that way? Not singular is kind of like a rare type of thing, in a sense. That's the origin of the word singular here. And the determinant of a random matrix is generically not going to be 0. It would be very unlucky if you got a determinant of 0 if the coefficients in the matrix were truly random. You have to think about it to try to make a matrix whose determinant is 0. So singular matrices are rare. Non-invertible matrices are rare in a sense. Non-singular are not rare. They are the typical case. It's typical that a 2x2 matrix would be invertible. Anyway, that's background. Let's get on to the eigenvalues and eigenvectors. You want to set the determinant of A minus lambda I equal to 0 and solve for the values of lambda. You weren't here the Friday before spring break. We talked about this, so you'll want to watch the video if you haven't yet. Lambda is going to be an eigenvalue of the matrix. And actually, the motivation for this, why we set the determinant of that matrix equal to 0, where I is the 2x2 identity matrix, something like that, was because we were looking for non-zero solutions to this equation. Non-zero solutions for V. Are there values of lambda? Are there scalar values of lambda that give you non-zero solutions for V? And that was equivalent to this equation. And that equation is going to have non-zero solutions for V whenever this matrix is singular, whenever its determinant is 0. I guess that's the main relevance of this kind of connection for us here. That's the motivation for setting this equal to 0 and seeing if you can solve for values of lambda that make that true. Is because you're looking for non-zero solutions for V, eigenvectors. Eigenvectors cannot be the 0 vector. We're looking for non-zero solutions. Eigenvalues can be the number 0. That can happen. We will see. Anyway, if I do this calculation, I need to imagine subtracting lambda times I from this matrix. In other words, subtracting that matrix from this one. You should practice this enough to do it well in your head. You just have to focus on subtracting lambda from the entries along the main diagonal, because these lambdas are only on the main diagonal here. The off-diagonal entries do not change. So we get a matrix 2 minus lambda, 7, -4, -9 minus lambda. I'm setting that equal to 0 and seeing if I can solve for values of lambda. Look okay, or is there a mistake? You calculate this 2x2 determinant in the same kind of way. Multiply the entries on the main diagonal. Subtract the product of the numbers on the off diagonal. This is going to be a quadratic equation in lambda. And this is what's called the characteristic polynomial of the matrix. This thing, well, let's simplify it first. Multiply this out, you get negative 18, let's see, minus 2 lambda plus 9 lambda is plus 7 lambda. Minus lambda times minus lambda is plus lambda squared. Don't forget about this other term. Look good? So we simplify that a bit, we get lambda squared plus 7 lambda plus 10 equals 0. This thing right here, that's called the characteristic polynomial of the matrix. Characteristic. Is that spelled right? Characteristic. I don't know why they don't just call it the eigenpolynomial. I mean, because I think, again, eigen is a German word that is somehow related to the word characteristic. Characteristic polynomial is what we typically call it in English, but you could have called it eigenpolynomial. Its roots are the eigenvalues. It's quadratic when your matrix is 2 by 2. So you can always use the quadratic formula to find the eigenvalues. In this case, you can actually factor it. I made the numbers nice. This can be factored as lambda plus 5 times lambda plus 2. So that's going to be 0 when lambda is negative 5 or negative 2. Can you see that down there? Negative 5 and negative 2 are going to be the eigenvalues. You can call them lambda 1 and lambda 2 if you like. With subscripts, you don't have to. If you wrote lambda equals negative 5 comma negative 2, I wouldn't mark it wrong. Technically speaking, they are two distinct numbers, so this is a little sloppy here, but we'll be okay with not being sloppy on homework or tests. Though I guess, at least with this example, I will continue to be a bit more precise here. If we've done things right, if we haven't made any mistakes, we should be able to find eigenvectors corresponding to these eigenvalues. Non-zero vectors that solve either of these equations. This one's the easier one to think about because you have 0 on the right-hand side. It's a homogeneous equation. Not a homogeneous differential equation, a homogeneous algebra equation. In other words, you can really just think about this matrix and think about these numbers as being coefficients of x and y in a system of equations where you have 0 on the right-hand side, 0 and 0. And in fact, if you've done things right, you can just think about one of those equations and not the other because they should be scalar multiples of each other if you've done it right. What would the first equation in this case be with lambda 1 equals negative 5? Replace the lambda there with negative 5. 2 minus negative 5 is 7. Let's go ahead and write it like this. That's 7. Plus 7y equals 0. Right, I got that second 7 right there. I'm not going to bother writing the second equation in the system, but let's just mentally check that it's a multiple of the first one for confirmation that we haven't made a mistake. We'd have negative 4x plus that times y, where lambda gets replaced by negative 5. Negative 9 minus negative 5 is negative 9 plus 5 is negative 4. We get negative 4x minus 4y. It would be a scalar multiple. The coefficients of x and y in this case are both the same. And that's equivalent to y equaling negative x. Again, the fact that I get this second equation that's a multiple of the first equation, negative 4/7 times the first equation, the multiple can be a fraction, means if I solve that system, I'm going to get infinitely many solutions. I'm going to get non-zero solutions in particular. But all those solutions, all those vector solutions are going to have the property that the second component is the opposite of the first. So from this, I can write down an eigenvector. I can pick x to be anything I want, but you might as well pick 1, keep it simple. And then y is negative x. A common mistake people make is they simplify this kind of equation to x plus y equals 0, and they jump to their eigenvector and think it's 1, 1, because there's a 1 there and a 1 there. But that's a mistake. It's a common mistake people make. Don't make it. Solve this equation for y in terms of x like that. That's telling you the signs have to be opposite in this example.
Yep, so how do you know which is negative, which one is?
It doesn't matter.
Okay.
I could make that one negative 1. If I did, that would be positive 1. There are infinitely many eigenvectors. Any non-zero multiple of this is also an eigenvector. It's not the only answer. That's a message to the graders too, okay? Got to alert them. If you picked, just to be crazy about this, if you picked negative pi, that would also be an eigenvector. As long as these components are the opposites of each other, that'll be an eigenvector for this eigenvalue. I need to emphasize that too. Eigenvectors always correspond to particular eigenvalues. This is not an eigenvalue for the other one. Excuse me, this is not an eigenvector for the other eigenvalue.
Was the general eigenvector, would that just be an x in front of the 1, negative 1?
So do you mean like this?
Yeah, so then like you factor out the x.
Yeah, that could be thought of as a general eigenvector as long as x is non-zero.
Yeah.
You don't want to consider the zero vector. Though it's a little funny, if you ever hear the term eigenspace, the zero vector does get included, but we're not thinking about that here. So if you're in linear algebra, you'll hear about eigenspaces as well. Oh, I didn't want to erase my matrix. Let's put it back up here. 2, 7, negative 4, negative 9. What about the other eigenvalue? Lambda 2 equals negative 2. Find an eigenvector corresponding to it. Replace lambda with negative 2. 2 minus negative 2 is positive 4. The 7 still is there. We get this equation. That 2 can be thought of as 2 minus negative 2. If I've done things right, I don't have to consider the other equation, because it's going to be a scalar multiple of the first one, but maybe just let's mentally check it again to confirm that it really is a scalar multiple. Negative 4 times x. Replace lambda with negative 2 there, you'll get negative 7 times y. The second equation would be negative 4x minus 7y equals 0. It would be negative 1 times the first equation. That's good. That means you haven't made a mistake. But you don't have to bother writing it. Solve this for y in terms of x. You would get y equals negative 4/7 x. So probably the simplest thing to do here for your eigenvector is to let x equal 7 so that y is negative 4. But any non-zero multiple of that would work too. Another common mistake people make here is they see this equation, they don't jump to this one, they just focus on this one and they think the eigenvector is 4, 7 or something. That's wrong. 7, negative 4 based on this would be the right thing to do. This now allows you to write the general solution. As a linear combination of particular solutions. What are those particular solutions? It shouldn't be a surprise that it involves E. It's E to the first eigenvector value, times t, negative 5t, times the eigenvector corresponding to that eigenvalue, this one, 1, -1, and then take the second eigenvalue, -2, write in e to the -2t times the corresponding eigenvector, 7, -4. There's a general solution. It's not the only possible answer. Any non-zero multiples of these eigenvectors would generate another general solution. It would look different, but it would still allow you to solve any initial value problem. Solutions of IVPs are unique. If I wrote a different form to the general solution, if I put, for example, 2, -2 there and 14, -8 there, then when I solve the IVP, the K1 and K2 would be different. However, when you simplify, you get the same answer. So it doesn't matter what general solution you write. If you've got an initial value problem, you will get the same final answer. What was the motivation behind this? The motivation for this was to try to find straight line solutions, which we are now going to think about in drawing the phase plane. If you look at the test from last year, there was a sort of a pseudo-proof on that test. It really wasn't a full proof. I just asked for brief reasons for each equation in that pseudo-proof, not sentence explanations. As to why functions like this, why in general functions of this form where lambda is an eigenvalue of A and V is a corresponding eigenvector, why are these solutions? It should be clear that they generate straight line solutions if they are solutions because V is a constant vector. So you multiply that constant vector by a scalar function of t, you're always going to get something along the same line to the origin. But why is that a solution? Make sure you study that. I'll probably talk about that on Wednesday. But make sure you study and try to figure out how to explain why that kind of function is a solution. Why do we do this? Anyway, let's draw the phase plane. First, make a big dot at the origin. That's your equilibrium point. Make sure you make that dot. Okay? It's important. Don't forget it. If you forget it on the test, that's at least a point off, maybe even 2 points off. This equilibrium point is a sink because both of these terms go to 0 as t goes to infinity, because you've got the negative coefficient of t in those exponents. But these eigenvectors correspond to straight line solutions. In other words, there's going to be a straight line solution along the line parallel to this vector going through the origin. This vector, 1, -1, is a vector that looks about like this. But erase that arrow. That's going to generate a straight line that consists of straight line solutions. But the arrows in the phase plane should head toward the origin here. I'm not drawing vectors when I draw that. I'm drawing arrows along a solution curve, a couple solution curves, heading toward the origin as t goes to infinity because you've got the exponential decay right there. What about this one? Draw that vector. It's not too far away from this one, so this picture is perhaps a little tricky. 7, -4. No, okay, well, let's see, it's more like this. If this were 7 out here, that would be -4 right there. Along that line, you're going to have straight line solutions, and you should draw arrows heading toward the origin. What happens in between? That's always the hard part. What happens for solutions in between these? Let me draw the nullclines in now to help me. I haven't talked about nullclines yet for this example. To think about the nullclines, you've got to go back to the original system, the original matrix. The original system based on this matrix was really dx dt equals 2x plus 7y, and dy dt equals negative 4x minus 9y. That was the original system based on this matrix. I wrote it in vector form on Mathematica over here. You should be able to translate between vector form and scalar form. Remember the x nullcline, where dx dt is 0, is where this thing equals 0. 2x plus 7y equals 0. Which is equivalent to y equaling negative 2/7 times x. This line has a slope of negative 4/7. A nullcline, which I think I'll just draw very lightly, would have a slope of negative 2/7. It'd be about like this. That's going to be the x nullcline, where dx dt is 0, and therefore solutions cross it with a vertical tangent, because the velocity vector for the solution curve has no x component, or 0 x component. So you can draw a bunch of little vertical lines along there. That's how you're going to cross. Whether it crosses going up or down, we've got to figure out still. The y nullcline is where this equals 0, negative 4x minus 9y equals 0. That's going to be equivalent to y equals negative 4/9x. Boy, these are all close together. That happens sometimes. Slope of negative 4/9. Let's see. Again, this had a slope of negative 4/7 here. Negative 4/9, that's going to be closer to 0, but not as close as this one. It's going to be in between. Oh boy. I'll try to pick a better example on the test where these are not so close together. You're going to cross that one horizontally. That's a y nullcline. Oh boy. Pick a point up in the first quadrant. What are the signs of dx dt and dy dt? If you pick a point in the first quadrant, x and y are both positive, making that quantity positive and this quantity negative. Dx dt is positive, dy dt is negative. The solution curve has to be pointing toward the southeast. The vector field has a vector pointing toward the southeast. Dx dt is positive, dy dt is negative. Solution curves have to be going toward the southeast here, which makes sense now looking at these lines. It's got to cross this one like this and then curve very quickly to cross this one like that before heading toward that solution.
For the y nullcline, it says negative 4x minus 9y equals 0. Is one of those supposed to be positive? Or
It comes from this equation here. That equals 0. If I add 9y to both sides and then divide by 9, I do get that.
okay. Yeah.
It's going to be an analogous kind of thing over here. I think I'll just fill in the rest here quickly. What about on here? It's probably going to go like this. It seems like we've got tangencies for solutions along this line. This line of straight line solutions also ends up being tangent to most solution curves, at least, as t goes to infinity. All the other solution curves, except for the ones along this line, are going to be tangent to this one as t goes to infinity. So that's getting the tangencies right. The nullclines help me do that. In general, if you don't draw the nullclines and you want to get the tangencies right, you have to figure out which line of straight line solutions for eigenvectors corresponds to the eigenvalue closer to 0. You'll see that in the reading. That eigenvalue, negative 2, is closer to 0 than this one is, negative 5. And because of that, that will end up meaning that solutions will be tangent to that straight line solution, that type of straight line solution as t goes to infinity. It's a fact in the book, you can read about it. You can make intuitive sense out of it too. I don't have the time for that today. That's something to look for in the reading and be careful about as you do the problems. All right, let's spend 5 minutes with this matrix exponential idea, which is not nearly enough time, but it'll get us going on an introduction to it. Let's go ahead and enter the matrix A here. Use the palette here. A equals, same example, 2, 7, -4, -9. Probably I should show you first that Mathematica can calculate eigenvalues and eigenvectors. Eigenvalues are -5 and -2. Corresponding eigenvectors are these two, which it looks like Mathematica picked the same answers as mine except multiplied by -1. Multiply that one by -1. Multiply that one by -1. You get Mathematica's answers. They are in the right order. This one goes with that eigenvalue, the first eigenvalue. The second eigenvector goes with the second eigenvalue. You can do this all at once with what's called Eigensystem. Eigensystem. These are the eigenvalues, these are the corresponding eigenvectors as lists. All right, what's this matrix exponential idea? Well, here's how you calculate it. MatrixExp. I don't have nearly enough time really to introduce this. Here's how you'd write it by hand. E to the A power, where A is a matrix. Huh? E to a matrix power? Yes, e to a matrix power. How do you make sense out of that? How do you raise e to a matrix power? Turns out the way to make sense of that is with a Taylor series. Without going into detail about exactly what this Taylor series means or how it's computed or how you know it converges, you can take any given square matrix, like our matrix A there, and square it, cube it, raise it to the 4th power, etc. You can multiply it by scalars. This is the identity matrix. Turns out that this is a good idea to define a matrix in this way, and Mathematica can compute it with matrix X. It's not super simple, but perhaps it's not surprising that the answer contains SMEs. What do you need to know about this? First thing you need to know is that the solution of the IVP written in vector form, dy dt equals a times y, and y of 0 equals y sub 0. The unique solution of that initial value problem can be written as y of t equals e to the t times capital A power, that's a matrix, times the vector y0. That's a matrix times a vector. That's the first thing to know here. Okay? Let me say 2 things before we go. This is very analogous to the scalar case. The scalar case dy dt equals little a times y, everything's a number here. Y of 0 equals y sub 0. That's got unique solution. Y of t equals y sub 0 e to the at. This is very analogous to that. The number a gets replaced by the matrix A. The number y0 gets replaced by the vector capital Y0. That's kind of cool. That's the next thing to know. The final thing I want to say is before I put this notebook on Moodle, I will add some more Mathematica code in here to check that. And also compare it with what NDSolveValue gives. And you'll see that you get the same answer. Okay, so that's the first thing to know about this. We're going to use this for flows in this kind of situation to make some pretty cool animations. And we'll do that on Wednesday. Okay? See you then.